Swayam Prabha. Digital India. Educated India.
So, the last two classes we basically saw some examples of systems where linear equations arise, okay, when you do the modeling. So, what we will do now is we will try and talk about some basic concepts, some abstract concepts, so that we can set the groundwork for doing the analysis, okay. So, these concepts are some things which you are familiar with, but we will possibly put them in a slightly different way, so that we can easily extend it from for different systems. So, that is the idea, and this whole thing basically can be looked upon as something which we talked about vector spaces, okay. So, we are just going to set some ground rules for doing the analysis and build the framework. Now, when you talk about vectors, most of you are familiar with vectors. If you look at physics, you have thought about vectors as having both magnitude and direction. And if you look at mathematics, people will talk about vectors as some kind of a structured array, a one dimensional array with elements, okay. Now, these are basically two different ways of representing a vector. The first one I will call it a geometric representation, where you think of a vector as a line with a direction. And the second one is an algebraic representation, where you do not have any sense of the geometry, but you just write it in terms of a vector, an array, okay. So, basically what I am saying is vectors can be represented as one, quantities with magnitude and direction, and this is what I call a geometric representation, and the second one is more of an algebraic representation, where we think of this as a one dimensional array, okay. So, this is what mathematicians use, this is what possibly people in physics use, but they are basically two different ways of representing the same quantity. So, if I look at the xy plane and I want to have a vector, let us say this is OP, OP is a vector, that is my geometric representation, okay. The end points of P, the coordinates of the point P are, let us say, x1, y1. x1 is the distance measured parallel to OX, y1 is the distance measured parallel to OY, okay. So, this is y1, this is x1. So, that is basically your coordinates of P, and in the geometric representation you have this line segment telling you that is your vector. In the algebraic representation, we will represent the vector as x1, y1. That is my algebraic representation, the two coordinates. So, to keep things simple, I have done this in a two-dimensional plane. You can think of this also in a 3 dimensions, x, y and z, and now this p will be somewhere here, and this will have 3 coordinates, x1, y1, z1. Okay. So, this is basically is projecting outside, but I can't draw it outside. So, I just project it here. Okay. So, the point P is specified by 3 coordinates. This is your vector, and the algebraic representation will be x1, y1, z1. This is the algebraic representation. That is what I was trying to say, that we are representing the same quantity either algebraically or geometrically. So, of course, geometrically we are able to see certain things, we are able to talk about things physically when you use the geometric representation. But sometimes our vectors may have maybe a very large size, the array may be of a large size. For example, if you are doing a simulation of a distillation column which has 40 trays or 50 trays, then you want to be your vector containing the compositions of all these different species will be 40 or 80 or 120, whatever it is, depending upon how many species are there. Okay. So, then you want to have higher dimensions. So, you want to be able to analyze problems in the higher dimensions. So, what we are going to do is talk about how the concepts which you are familiar with in for 2-dimensional vectors, for 3-dimensional vectors can be extended to higher dimensional vectors, okay, where you lose the physical insight of things like length and angle and all that, but same idea we want to extend it there. That is where the concepts from defined in the algebraic representation will be extended to the from geometric to algebraic, okay. That is what we are trying to do. So, algebraic representation helps you go to a larger space, okay, because the vectors could be of a very large number of elements could be there in the vector. You are not restricted to 3 dimensions, because physically you can only visualize 3 dimensions or maybe 2 dimensions. More than that, 4 dimensions I can visualize, okay. So, you lose that physical interpretation, but you get into more of mathematics. So, what we want to do is set some basic rules. I am going to talk about some concepts called closure. So, closure means if I have a set of elements which are closed under an operation, okay, then when I take 2 elements and subject it to that operation, I should get a third element which belongs to the same set, okay. That is what I mean by closure. So, basically we have a set of elements is closed under an operation if 2 elements from the set subject to that operation gives a third element belonging to that set, okay. The operations that we are talking about are addition, subtraction, multiplication, division, okay. So, what are the operations? subtraction, multiplication, and division. These are 4 operations that we normally talk about. So basically, if I look at set of integers and I look at the operation of addition, if I add 2 integers, I will get another integer. So the set of integers is closed under addition. Okay, that's what I mean. So set of integers is closed under addition. Why? Because adding 2 integers gives a third integer. But the set of integers is not closed under division. If I take 2 integers, if I divide one by the other, I may not get an integer. Okay? And whenever we talk about division as an operation, we have to make sure that we don't end up dividing by 0. Okay? So when you divide by something, make sure that something is not 0. So division is always by some non-zero number. So this is not closed under division. Okay, because if I take 2 and 3, divide one by the other, I get 2 by 3, which is not an integer. So 2 and 3, 2 by 3 is not an integer. So basically, set of integers is not closed under division. I want to generalize this concept to what is called a field. Field is basically a set of numbers or elements which is closed under all the 4 operations: addition, subtraction, multiplication and division. Okay? Basically, set of numbers which is closed under addition, subtraction, multiplication and division. Okay. So an example of a field is a set of real numbers. Okay. So R is the set of real numbers is a field. Similarly, C, set of complex numbers is a field. You add 2 real numbers, you will get a real number. You multiply, you subtract, you divide, you will get a real number. Okay. So basically, set of real numbers is a field, set of complex numbers is a field. You take 2 of them, subject it to any operation, any of these 4 operations, you get back another element belonging to the same set. So this is, so whenever we say field, you can think of it as set of real numbers or complex numbers. Okay. Now, 2 concepts of scalar multiplication. So, you take a vector and you were to multiply it by a scalar which belongs to the field. Scalar will be belonging a real number belonging to the field. Okay. Then what are you going to get? You are going to get another vector which will have a magnitude decided by the alpha times, okay, and the direction will change depending on whether alpha is positive or negative. Okay. So, let us say we have a vector u is a vector and k is a scalar. Okay. So, k times u, this is a scalar multiplying a vector, gives me a vector whose magnitude is absolute value of k times the magnitude of u. Okay. So, u has a magnitude, so ku has a magnitude is k times that, okay, and the direction of u is reversed if k is negative. That is my physical geometric way of thinking. Okay, if k is negative, the direction is in the opposite direction. Okay, that is what you are used to thinking. In the algebraic representation, what will I have? If my original vector has coordinates x1, y1, my k times the scalar multiple of this will be kx1 have coordinates kx1, ky1. Okay. So, in the algebraic representation, if x1, y1 are the coordinates of u, then ku will be kx1, ky1. Okay. So, that is the algebraic way of looking at things. Now, couple of things we will do is scalar multiplication, and the other thing we do is vector addition. When it comes to vector addition, I mean the geometric way of thinking is you use something called this parallelogram law. You draw one vector, supposing you want to add two vectors, supposing you have OP and OQ are two vectors, okay, and let us keep life simple and do things in a two-dimensional plane, OP and this is OQ. Okay, OP and OQ. So, what do you normally do in the parallelogram law? You keep OP as it is, this is OP, and you redraw OQ such that instead of starting at 0, it starts at the terminal point of OP. Okay. So, what I am drawing is I am drawing this vector parallel to itself here. So, this is OQ, this is parallel to OQ, same length, same direction, and the vector sum is given by this vector is OP plus OQ. Okay. Again something you are familiar with. That is the geometric representation. In the algebraic representation, what happens? So, this is the parallelogram law, right? This is law. Okay, I am not going to write it down. So, all I have done is written OP, drawn OP exactly the same, and this vector is parallel to OQ on same magnitude. In the algebraic representation, so if you have x1, y1 as one vector and x2, y2 as another vector, so this is OP and that's OQ, the sum, the vector addition gives a vector x1 plus x2, y1 plus y2. These are the new coordinates, okay, and that's possibly easy for you to see because this distance was x1, so as x1, this is x2, this projection will be x2, so x1 plus x2 will be here and y1 plus y2 is the y coordinate, okay. So these are again things which you are familiar with and I am just possibly making you recap whatever you have done. If you talk about a vector space, or a linear space, this has two things. One is a field which is a set of real numbers or complex numbers. Okay, and it has a set of vectors which are closed under scalar multiplication and vector addition. Okay. So this set, the field is basically a set of real numbers, it has scalars, okay. This is giving you the scalars. I need the scalars because what do I mean by closed? A set of vectors closed under scalar multiplication. If I were to multiply the coordinates by a scalar, I will get another vector belonging to the same space. Similarly, if I take two vectors, I add them, vector addition, I will get a third vector which is also belonging to the same space. So just to give you an idea about what I mean by space, so you look at those vectors which we drew in this two-dimensional plane, okay. Each vector had two elements, x coordinate, y coordinate, x1, y1. So when I take two vectors, add them, I will get a third vector which also has only two elements. So it belongs to the plane, the same space. If I take a vector which has two elements, two coordinates and multiply by scalar, I will get another vector which again has only two coordinates, okay. So it belongs to the, so the space is, I am talking about vectors which have only two coordinates, or you can have a vector which has three coordinates or four coordinates, okay. So basically what I mean is, if you take a vector, consider a vector which I will say belongs to R2, okay. Now what is R2? R2 is basically space of vectors which has two coordinates, there are two elements and both of them are real. R is for real, 2 is for number of elements, okay. So this is basically space of vectors with two elements, like vector in a plane, Okay. So, if I take two vectors in a plane, I'll get another vector in a plane. I have two coordinates for each of them. I get a third vector with two coordinates. Multiply it with a scalar, I'll get another vector with two coordinates. So, it all belongs to the plane. Okay. That is what I mean by. So, this R2 basically is a vector space, because it has a field which is, let us say, real numbers, vectors which have two coordinates. Add two vectors with two coordinates, I get a third vector with two coordinates with real numbers. Multiply by scalar, I get another vector with two coordinates, okay, which are real. Again, it belongs to the same space. So, it is closed under scalar multiplication and vector addition. Okay. So, that is the basic idea of vector space or linear space. I mean, you can extend this to 3-dimensional, 4-dimensional. So, basically what I am saying is, if U1 belongs to R2, U1 is just some vector, superscript is just some U1, U2, U1 is one vector, U2 is another vector, okay. Then C multiplied by U1 also belongs to R2. C is some scalar, okay. So, this is the scalar, this is the vector. So, on multiplying a vector by scalar, get a vector belonging to R2. Similarly, U1 and U2 also belong to R2. This has two elements, x1, y1, this has x2, y2, I add, I get x1 plus x2, y1 plus y2, again it has two elements, okay. And so, this is x1, y1, x2, y2, when you add it, I will get x1 plus x2, y1 plus y2, and you can do the same thing. You can do C1 U1 plus C2 U2, scalar multiple, because scalar multiple gives you a vector, and then this also gives a vector, add, again you will get, this also belongs to R2. So, that is what I mean by closure. I am not going to get a vector in R3 which has 3 elements, okay. So, I want to move on and talk in terms of certain quantities like distance, length and angle between vectors, again things which you are familiar with, okay. So, if I have two vectors, consider U1 as one vector x1, y1, okay, and U2 is another vector x2, y2, okay. I have two vectors and you want to talk about the distance between these two vectors. The thing which you have been using all along is what is called the Euclidean distance, where you use something like Pythagoras theorem and then find what the distance between two vectors is, okay. So, the distance between U1 and U2. So, I am going to try and stick to this notation where the superscript tells you the ith vector, subscript tells you the coordinates, okay. The subscripts are used for coordinates which are the elements in the vector, and superscript is for the ith vector. What is the distance between these two? We write it as x1 minus x2 whole squared plus y1 minus y2 whole squared. This is the distance which you are comfortable with, okay, and this is called the Euclidean distance, okay. The other concept which comes is the concept of length of a vector, So, when you talk about distance, you talk about distance between two vectors. When you talk about length, only one vector is there. So, the length of so this is distance. The other concept is length, where, and I am going to use this symbol for length, okay. Two lines here, two lines to the right, two lines to the left. This is basically the distance, the length of a vector is basically the distance of the terminal point from the origin, okay. The origin will have coordinate 0, 0. So, this will be basically x1 squared plus y1 squared for u1. This is basically distance of the final point from the origin, okay. Similarly, norm of u2 or length of u2 will be square root of x2 square plus y2 square, because this is u2, distance of this from the origin, okay. So, length of u2 now the other concept is that of angle, and what you are used to is this concept of dot product to find the angle. If I give you two vectors, you take the dot product of the vectors and then divide by the magnitude or the length of each vector, and you get cosine of the angle, right. So, basically the angle is given by the dot product of u1 and u2, and how does this work? Now, two vectors, what you are trying to do is you are trying to project one vector on the other. Basically, that is what we are doing when we take the dot product, okay. So, we take this dot product of the two vectors, and you know how to do that. This will be the magnitude of u1 multiplied by the magnitude of u2 times the cos theta. Again, this is something which you have done in physics. What we want to do is, since we want to let go of this restriction to two-dimensional vectors and three-dimensional vectors, which is what you have been using in physics most of the time, and we want to talk about higher dimensional systems. For example, that heat exchanger problem, we wrote it was a batch reactor problem. We had 4 different concentrations of A, B, C, okay. So, the element has 4 vectors. So, it is not the same as the physical direction. The mathematical, the algebraic representation has 4 vectors, has 4 elements, sorry. The algebraic representation in the batch reactor problem has concentration. Each of these elements is a concentration, but there are 4 elements. So, it's a mathematically it belongs to R4, okay. So, if you want to analyze systems with 4 elements, we want to be able to extend whatever we have done here to larger dimensional spaces. The concept of distance, length and angle, I want to extend to higher dimensional spaces, okay, and that is what we want to do now, okay. We want to extend these concepts to higher dimensional spaces like R4, okay. This batch reactor example, okay, where it is difficult to visualize things geometrically, but we will use that for low dimensions. I showed you the equivalence between geometry and algebra. So, now I will just directly go to algebra, okay. Okay, so let me just say distance is what I am going to call metric. Now, length I am going to call norm, and the dot product I am going to call inner product. So, these are the generalizations of what we have already seen. You talked about distance, the Euclidean distance. I want to generalize it into a concept called metric. Metric basically you have to think of as distance, okay. It is a general way of representing metric, distance. Norm is a general way of representing length. So, norm basically means length, and I will tell you why it is general. And you are used to dot product, we will call it inner product, okay. So, that is basically the generalization or the extension. So, this is I want to talk about first we will talk about metric. Metric space. So, metric I told you is basically concept of distance, okay. You saw one example of the definition of the distance, square root of x1 minus x2 square plus y1 minus y2 square. But is that the only way in which you can define distance? Are there other ways? That is a geometric way of looking at it, distance between 2 points, okay. But since anyway now in higher dimensional space I can't think of it geometrically, I want to know, is there any other way I can define distance, okay. Since we are looking at, so basically when you talk in terms of distance, there are certain properties which this your definition has to satisfy, okay. So, what I am going to do is write down the axioms which I am expecting the distance to satisfy, and if you can think of a definition which satisfies those axioms, then that is a candidate for a possible definition of distance, that is possible for a candidate for a metric, okay. So, basically I am saying we want to be clear that the Euclidean distance is not the only possible way of defining distance, there can be other ways of defining, okay. So, the Euclidean distance the only way to define distance. The or metric must satisfy some axioms, okay, and if these axioms are satisfied, we have a definition for a metric, okay. So, let me explain to you what I mean by these axioms. So, since we talk about two vectors, we need two vectors first of all. Yeah, u and v are two vectors, okay, and I am saying we expect the distance between u and v to be greater than 0 for u not equal to v. You are talking about distance between Chennai and Calcutta or Calcutta and Chennai, distance is the same, okay. We are not looking at the vector, we are looking at distance. So, it's 1000 kilometers that way, it's 1000 kilometers the other way also, okay. So, that we will come to that later, is always going to be positive. If, sorry, I was talking about the next one. If u and v are different, you are going to have a positive value always, not a negative value. If d of u comma v equals 0, this implies u equals v. Distance of Chennai from Chennai itself will be 0, okay. Other thing is d of u comma v must be equal to d of v comma u, that is what I was talking about. Distance between 2 points A and B the same as the distance from B to A, okay, that is common sense. And then you have a triangle inequality, which is d of u comma w is less than d of u comma v plus d of v comma w, okay. So, basically this tells you distance always has to, if you can think of some definition of a distance which satisfies these 4 properties, these 4 rules, these 4 axioms, then I mean these are basically common sense axioms, right. Distance will be positive, distance will be 0 only with the same point, distance between A and B is same as B to A, and the triangle inequality, one side of a triangle is always lesser than the other 2 sides. So, any definition which satisfies these axioms is a possible metric or can be used as a possible metric, okay. So, now, so I have x1 y1 and x2 y2, let us say this is v and this is u. I am just going to say that I am going to look at d2 of u comma v, which is the square root of x1 minus x2 squared plus y1 minus y2 squared. This is your classical Euclidean distance definition, okay, and that I am calling d2. But the point I am making here is this is not the only way I can define metric. I can define metric in some other way also. For example, and this is what you have to verify, d1 of u comma v is x1 absolute value of x1 minus x2 plus y1 minus y2, the absolute value. What I am doing here, I am squaring it and then taking square root, taking square root. Now I am not doing any squaring, I am just taking the absolute value of the difference x1 minus x2 and y1 minus y2. And there is one more, yeah. So this is an alternative method for us to possibly define. This is going to be valid provided this definition satisfies these axioms, okay. And this does not have that geometric significance of the distance that you are comfortable with. Now, for example, does this definition satisfy the first one? Because its absolute values, it will always be positive. What about the second one? If u is equal to v, then it is going to be 0 because x1 will be equal to x2, y1 will be equal to y2. Okay. What about this third one? It is also satisfied because you just have to flip and you take absolute value anyway. And similarly, you can argue and show that it satisfies the third one also, the last one, the triangle inequality. So, because this particular definition satisfies all of this, this is also a possible definition for the metric. Okay. So, this is a possible definition as it satisfies the axioms. Okay, you have to do some work to get the third, the last axiom. The last point I want to make today is these axioms do not involve the concept of scalar multiplication and vector addition. There is no question of vectors being added, there is no scalar being multiplied. Okay. So, what I am trying to point out is that I can have a definition of metric in a space which is not a vector space. In the vector space, I said it should be closed under scalar multiplication, vector addition. Here there is no concept of scalar multiplication and vector addition, right. In these there is no vector addition, there is no scalar multiplication. So, a metric can be defined, does not have to be defined in a vector space, it can be defined in a general space. Okay. So, that is the last point I want to make, then we will generalize it and talk about other things. So, since the axioms do not involve scalar multiplication or vector addition, we can define a metric in a space which is not a linear space or a vector space, because linear space I said was closed under the addition of scalar multiplication and vector addition. Okay. So, here there is no question, that is the only thing I want to make. We will continue this and we will go on with how to generalize the definition of length and angle.